Today we are going to learn about mastering ROC curves for model evaluation. We will explore how to interpret and utilize ROC curves effectively to assess model performance, especially in imbalanced datasets.
Welcome to our exploration of ROC curves. ROC, or Receiver Operating Characteristic Curves, are graphical plots that illustrate the diagnostic ability of a binary classifier system as its discrimination threshold is varied. They are fundamental in the field of statistics and machine learning for evaluating the performance of classification models. Historically, ROC curves originated from signal detection theory, developed during World War II for radar operators to discriminate between enemy targets and noise. In our session, we'll delve into how ROC curves are constructed, interpreted, and utilized, setting the stage for understanding their critical role in assessing model performance, particularly in classification tasks.
The area under the curve, or AUC, is a crucial metric derived from ROC curves. It quantifies the overall ability of the model to discriminate between positive and negative classes. AUC values range from 0 to 1, where a model with an AUC of 0.5 performs no better than random chance, while an AUC of 1 indicates perfect classification. The AUC provides a single scalar value that summarizes the performance of a model across all classification thresholds, making it a powerful tool for model comparison. By understanding and interpreting AUC values, we can make informed decisions about which models are most effective for a given classification task. ROC curves are indispensable when evaluating binary classification models. They provide a comprehensive view of a model's performance across different decision thresholds, highlighting the trade-offs between true positive rates and false positive rates. Unlike single-point metrics such as accuracy, ROC curves offer a more nuanced understanding of how models behave under various conditions. This is especially important in fields like medical diagnostics or fraud detection, where the costs of false positives and false negatives are unequal. By visualizing performance in this manner, ROC curves enable practitioners to choose the optimal threshold for their specific context. Plotting ROC curves involves several key steps. First, we prepare our data, ensuring we have binary labels and predicted probabilities. Next, we select a series of thresholds to evaluate. For each threshold, we calculate the true positive rate, TPR, and false positive rate, FPR. These rates are used to plot points on the ROC curve. As we connect these points, we form the ROC curve, which gives us a visual representation of model performance across thresholds. By examining the curve shape, we can gain insights into the balance between sensitivity and specificity, guiding decisions on the best threshold to use for deployment.
Interpreting a ROC curve involves analyzing its shape and position. A curve closer to the top left corner indicates a better performing model, as it suggests a high true positive rate and a low false positive rate. The point on the curve nearest the 0,1 coordinate is often considered the optimal threshold, balancing sensitivity and specificity. However, shifts in the ROC curve can occur due to changes in data distribution or model biases, requiring careful interpretation. Common pitfalls include over-reliance on the curve's appearance without considering the context or costs associated with classification errors. While ROC curves focus on the trade-off between true and false positive rates, precision recall curves emphasize the balance between precision and recall. Precision recall curves are particularly useful in imbalanced datasets where the positive class is rare, as they provide a clearer picture of model performance in such scenarios. In contrast, ROC curves can sometimes present an overly optimistic view in these cases. Understanding the differences between these curves allows practitioners to select the most appropriate evaluation metric for their specific problem, ensuring they make informed decisions based on the nature of their data and task. Imbalanced datasets, where one class significantly outnumbers the other, pose unique challenges for model evaluation using ROC curves. In such cases, the AUC can be misleading, as a high AUC may still correspond to poor performance on the minority class. To address this, practitioners can employ techniques such as resampling, synthetic data generation, and adjusting classification thresholds to improve the balance between classes. By carefully interpreting ROC curves and considering alternative metrics like precision recall curves, we can ensure a more accurate assessment of model performance in the presence of imbalanced data. Numerous tools and libraries are available for visualizing ROC curves, each offering unique features and integration capabilities. Popular options include Python libraries such as scikit-learn, which provides built-in functions for calculating and plotting ROC curves. These tools allow for customization of plots, enabling users to tailor the visualization to their specific needs. Additionally, integration with machine learning frameworks like TensorFlow and PyTorch streamlines the process of evaluating model performance. By leveraging these tools, practitioners can efficiently generate and analyze ROC curves, enhancing their ability to interpret and communicate model results effectively. ROC curves have broad applications across various industries. In healthcare, they are used to evaluate diagnostic tests and predictive models, assisting clinicians in making informed decisions. In finance, ROC curves help detect fraudulent transactions by assessing the performance of classification models. Marketing professionals utilize ROC curves to segment customers and predict behavior, optimizing targeting strategies. Moreover, ROC curves play a vital role in automated decision-making systems, where accurate classification is critical. By providing a visual and quantitative assessment of model performance, ROC curves contribute to more effective and reliable outcomes in diverse fields. Despite their utility, ROC curves can be misunderstood or misinterpreted if not approached with care. A common pitfall is misreading AUC values without considering the context, such as data distribution or imbalance. Practitioners may also overlook how imbalanced classes can skew ROC curve results, leading to overly optimistic interpretations. Additionally, relying solely on ROC curves without considering other evaluation metrics can result in incomplete assessments. To navigate these challenges, it's essential to combine ROC analysis with other methods, adjust for data imbalances, and maintain a clear understanding of the model's application and limitations. As the field of machine learning evolves, so too do the techniques for ROC curve analysis. Advanced methods include multi-class ROC analysis, which extends traditional binary ROC evaluation to more complex classification tasks. Additionally, ROC curves can be employed for model selection, helping identify models that offer the best trade-offs for specific applications. Enhancements in interpretability and visualization techniques allow for more intuitive analysis and communication of results. As we look to the future, innovations in ROC analysis are likely to continue, driven by the growing complexity of data and the need for more sophisticated evaluation tools. As we conclude our journey into mastering ROC curves, let's recap the key points we've covered. ROC curves are vital tools for evaluating the performance of classification models, offering insights that go beyond mere accuracy. By understanding and utilizing AUC, interpreting curve shapes, and navigating the challenges of imbalanced datasets, you can enhance your model evaluation skills. I encourage you to apply these concepts to your projects and continue exploring resources for further learning. Mastery of ROC curves will empower you to make informed decisions and drive success in your data-driven endeavors.